Yes. So, I guess I'll give a formal introduction. So, Dr. Wood, as he alluded to, has done lots of wonderful things at NIST. And I think it was a year and a half ago, 2 years ago at this point, that you moved over to CHIPS. I can't remember.
Formally about a year and a half ago.
Yeah,
so but it's been longer.
He moved over to the NIST CHIPS Act office, which is one of the entities sort of responsible for figuring out how to wisely invest CHIP tax funding and make sure the U.S. is competitive in semiconductor manufacturing. So, Deputy Director Lynn.
Hey, thank you so much. I'm really happy to be here. So I'm trained as a little bit about me. I'm trained as a chemical engineer. I've worked mostly in material science, polymers, and soft materials. I was at NIST as a division chief in the material science and engineering division when the Materials Genome Initiative was initiated. And that was a very exciting time. And this program and many others very similar have been extremely exciting. And even though we've made so much progress around materials discovery, high throughput experimentation, now the use of AI and machine learning, all towards a lot of the projects that were very exciting that I'm going to see, I saw that you're going to go through. We really did not fully understand the full power of what was possible during the MGI as we do today. And so since I've been at NIST my whole career, and as I said, I feel like I'm a bench scientist at heart, or that's how I think, how I identify myself, even though mostly I was in more like a lithography and low-K dielectric materials, more of those type of systems. So when the CHIPS Act was passed, and just to be honest, for us at NIST, we had been preparing. We had heard about it, of course. We were tasked to do some preparations for whether or not this act would pass. And I didn't think it was going to pass. I thought it was just, so that goes to show how much we know as career federal employees. Mostly I learned that the individuals who are behind it are not people you bet against, is what I finally realized. But the fact that they put the entire Chips for America Act, it's $52 billion, $50 billion of it inside an agency, the National Institute of Standards and Technology, was just kind of mind-blowing. Our annual budget is about $1 billion per year. And so $50 billion all at once is a little bit different. We also didn't have any of the infrastructure you would normally associate with running incentives programs for financial awards for huge companies, global companies. And then there's $11 billion for R&D, which I'll get to in a second. But as we just started to think about it a little bit more, of course, we were very proud to be identified to be stewards of this major program. And that derives primarily from our mission. Sure, we're awesome scientists. We have a great laboratory. Hope all of you have had a chance to visit NIST at some point. But the main reason for the Chips for America Act is really because of our mission. So one is in the Department of Commerce, which is we are focused on industry and economic development for the country. And so that's where the semiconductor industry primarily lies. The second part for NIST is that the first words of our mission are promote innovation and industrial competitiveness. And so that means since our founding in 1901, we are entirely focused on promoting innovation and working with industry. And the way we do that is primarily through measurement science, fundamental science, standards, and technology. And so NIST covers a huge range of technologies, not just material science, not just semiconductors. We bioscience, biotechnology. We're responsible for the Surfside Condo official investigation, cybersecurity, and AI safety. It's a huge range of activities that we're involved in and often leading into the future because of the importance of this of its importance on the nation and our nation's innovation infrastructure. Okay, so with that background, I'll just let you know. I'm just going to go a very high level, try to give you a sense of just what's happening, how you might fit in, and where you might make a difference. And so please ask questions along the way. I didn't put a whole lot of details in here, and I'm happy to go down any different directions or rabbit holes you'd like to. So one thing I learned is that now I have to put this disclaimer up all the time. So it turns out if you have, in our case in R&D, $11 billion that we haven't fully spent yet, everyone becomes your friend and they listen to every word you use. And so this basically says if I say something until it's in writing in an official notice of funding opportunity, then I may be wrong. Okay, so And so those are the official policy documents, but yeah, that turned out to be a lot more necessary than before. Okay, so how many of you are familiar with the semiconductor industry, not semiconductor materials? Okay, say like you track it all the time, every day. Okay, you know the full process flow, you know what that means? All right, okay, so basics. So semiconductors, we're all aware of, especially you all, since especially for the nature of this program and the tools that you use. But to put it in some basic economic terms, you know, the semiconductor industry in sales is over 500, nearly $600 billion in sales in 2022. And the industry expects to grow to a $1 trillion industry by 2030. There's 300,000 plus workers in the US. And I'll get to the future in a second, but because you're seeing so much attention to building new fabs in the United States, that number is expected to double. Okay. The US share of global semiconductor manufacturing in 1990 was 37%. There were a number of different companies that made semiconductor chips, Intel most prominent among them, but there are others. At that time, IBM also was manufacturing chips, for example. And then in 2021, that was down to 12%. And if we go to the leading edge semiconductor chips, the ones that are the most capable, the ones that are in NVIDIA cards, for example, it is basically zero. They are all made in Taiwan, okay? And Korea. Korea and Taiwan are the only two places that can produce the chips that everybody wants right now. Okay, furthermore, if you want to build a new fab inside the United States, it's usually a 4 to 5 year process and will cost you at least $10 billion. That's for each one. And so at the current state, there's about 15 to 20 being built in the United States right now. And so that already exceeds the CHIPS Act funding, $50 billion, $52 billion by quite a lot. So in this world, $52 billion is not very much, actually. So this picture is sort of a canonical integrated circuit. This picture up here is as an EUV, extreme ultraviolet lithography machine. This is an incredible machine. It's basically a boxed synchrotron with that allows you to manipulate optics on a nanometer scale. And that one instrument costs about $300 million, and a fab might need 4 or 5 of them. Okay. The first one just got shipped to Intel earlier the NA, high NA ones, which is what this is, just got shipped a few months ago. A fab looks something like that. So this is, I'm sure have all you worked in a clean room before, like a class 100, class 2. So this is a class 10 clean room that's this size. So if you go to Intel and their old fab, you can't see the end of the hall of the bay inside this fab. So humans are not allowed in this bay. The wafers are carried around in carriers. It's almost entirely automated until something breaks down. And this is all necessary to produce this integrated circuit. Okay? So there are thousands of steps, processing steps. Some of the steps you're working on in your hands-on experience this week will be the same as the ones in here. It's just that they're highly controlled because each of those steps has to reach basically atomic level control over an 8-inch wafer. And so this is really the most complex manufacturing process ever invented and deployed by humans. So one of the crazy things is that I studied lithography, the materials that are used to pattern down to 2 nanometers, 4 nanometers now. They're polymers. There's multiple components to it. This is a very common theme for what you guys are going to do. And because we understood all the details of the chemistry, physics that go into patterning with this type of technology, lithography, I'd say I just think it's even more like magic. I just cannot believe it works on the scale that it does, okay? And so if any of you have taken chemistry, like every step you have a yield, and every yield reduces what you get at the end. This process has thousands of steps. You have to finish with greater than 90% yield with atomistic defects being a problem. So this is just mind-boggling overall, okay? Now, why would we go to so much trouble to do this? So you have to make billions of dollars of profit to justify spending billions of dollars into a factory that you're betting on, expecting to make money afterwards. And that's because semiconductor chips, not just the most leading edge ones, are in basically every product and every tool that we're using right now. when the CHIPS Act was started under discussion, AI was on the table, but it was kind of in the background. It was like many years away. And now you see in the most recent just year and a half, 2 years, just the complete explosion of just activity, everyone desperate to try to find the most computing power at the most power efficiency that they can. But every phone has a chip, every car has hundreds of semiconductor circuits in it. Our toys have circuits in them, our appliances, our road sensing, all these things have semiconductors in them. And so it was very imperative and very scary for the country that we were not able to make any of the leading edge chips and under 15 and shrinking 10% of the overall semiconductor supply. Okay. And so this confluence of factors is what drove toward this major push that is bipartisan, bicameral, with the industry support. It has a shared interest with partner and allied nations across the world. Everyone's trying to figure out how to get there into the future. Okay, and then just, that it's at NIST, just across the beltway. And for us who are really career lab scientists, it was mind-blowing. Okay, so what is the overall vision for Chips for America? First one, I think, is from the main part is economic security. So during the pandemic, there's a very famous panic about the fact that cars could not get semiconductor chips, which was the main reason for why the prices escalated. So that showed that the supply chain, in this case, not leading edge semiconductors, but mature node, what we call mature node, legacy node, still completely insane, like, 20 nanometer control over 8-inch wafers, but considered like afterthoughts in terms of price, we had vulnerabilities to that supply chain. The second one is national security. The increased competition with China is a very clear, obvious change that's happened. And so not only is it our automotive industry and our compute industry, it is also our national security. So the DoD has a lot of needs that they have, and all their supply chains was also increasingly going overseas. And the third one is the future innovation. So if this is true, then here's the other mind-blowing thing. Your fab you just spent $20 billion on might be obsolete or not making the profit it was in 4 to 5 years. So you have to do it again. And so each one gets more expensive. And that's how the semiconductor industry has operated for the last 50 years. So they build a fab, they have to retire it into other types of products, but then they have to build a new one with each increasing step just getting more and more expensive. Okay. All right, so what else has changed? So geopolitical landscape, I think that's pretty clear. It was very substantial. It was very, very quick on this type of time scale. Bipartisan, common goals, interests. Unfortunately, that's also a little bit unique at this point. Embrace of industrial policy, like it used to be, we would twist ourselves into pretzels to not say we had a policy to help industry, even though that was our mission in our agency. So that is gone, but it is very specific on two things. The first one is that it is on foundational technology, things that you have to have the capacity. It's like, you didn't have access to water, right? Something like clean water to do that. So semiconductor technology, because it is ubiquitous and because it is constantly being pushed forward, that makes it a foundational technology. And the second one is to embrace or to realize that economic security and national security were never off the table. But now, because the world is so interconnected and that technology is one of the primary differentiators for security, then it became a priority, even more so than before. Okay, so what this meant is that some crazy things happened, okay? People who are in competitive postures, Hatfield-McCoy level competition, Romeo and Juliet level competition. Okay, in this industry, it is that cutthroat. So when I would go to industry meetings before, I would have different industry, because we were neutral, different industry parties would do things like, yeah, I said this extra loud in the hallway to try to feed false information to my competitor about what we were doing. right? This is crazy kind of things, especially for, research, open research oriented people. But because of the priorities were aligned, then the industry started to talk to each other. Competitors for the first time would sit down about what are shared interests to be able to meet the goals of the country. Now, that kind of thing, to be fair, has happened before through things like Semitech or other industrial consortia, but not at the level of depth and urgency and camaraderie, honestly, in the last year and a half. The only place where competition is even more fierce than industry is in academia for some reason. And so like a lot of institutions would be in competition with each other as normal proposal processes would be. But the nature of the times today and the expense of what we need to do means that there's much more coordination. At this point, it's between community colleges and four-year colleges, high schools and higher ed. But we need much more cooperation. This program is a very good example of that. We are able to do that, but at a scale that is far beyond that than we have done before, and for a much more in-depth understanding of how to find collective wins as opposed to just superficial ones. Okay, another place is government agencies. We don't always work the best together either, okay? And so that has had to change because of the scale of the problem, and the dollars are really big, but they're not big enough. And so we do have to work together to be able to align our efforts for the benefit of the country. Okay. Last one is that there are cross-sector conversations and ideation. So you see biotech and medical device companies talking even more to semiconductor companies. You have AI companies who honestly, a lot of them had no idea how their compute hardware worked. They just buy Amazon services and it's magic until they tried to, like in Silicon Valley right now, just tell you a famous story is Sam Altman, CEO of OpenAI. He's got a lot of pull right now. He goes, for OpenAI, I need more compute. So maybe I should just, be like Tesla and Elon Musk and just build my own compute center. So he goes around Silicon Valley. So what would it take? And then he understood on that tour just how complex it is to even build these things, and that he would probably need to raise $1 trillion to just get in the game and start 50 years behind, right? So this is not just a commodity. This is very, very intense, high-end technology and engineering. But those conversations are ongoing. So it's not just a bifurcation of like, oh, I just buy the service and it magically appears. You have to understand the whole system. Okay, and then semiconductors are not the only platform for the future. So AI, I think, is an obvious next one. This is a place where all of you have a role to think about. Biotechnology is certainly another one. Just our energy and power, of course, is a clear one. So just you can think about the major ones, and they're pretty well documented. They're just not easy to address. Okay. So if I could leave you with just a couple of thoughts for the rest of what I go through. Number one is the world has changed. Okay, traditional ways we think about disciplines and how we think about using science and technology, how do we contribute to it, are very different. The world's more interconnected, more competition, more complex. The second thing is that it is very much worth your while to understand at least how the bigger picture works. Okay, so for example, out of those 1,000 steps, they all depend on each other. You can't just change one. If you want to change one material in those 1,000 steps, which is going to what you're about to do, and it turns out some critical step that costs $100 million just can't do it, then it's just dead. It's just not economically viable. So it's very important to be able to understand the manufacturing process and the economic and business landscape to factor into how you think about like introducing an innovation like a new material. Okay. And the third thing is there are a huge growing number of opportunities. This is kind of a chaotic time about no one knows exactly how it's going to go. I'll show you how we're going to try to harness that with the government support. But this is a time to really start thinking really about what could be done better and what tools can be brought to bear on that. Okay. All right. I'm going to go into like bureaucraties and program stuff. Any questions so far?
So we do actually have
Okay.
one question from online. And it goes back to this question about the semiconductor industry in the U.S. economy. What percentage does nanotechnology account for now beyond the miniaturization paradigm? I wonder what's involved with the nanoscaling versus the micro and macro scales to this issue.
Yeah. Nano is a lot broader, of course. It covers a lot more different topics and areas. It's really been a rally around a type of science to push boundaries, which is how I see the nanotechnology initiative. Basically, every step in this industry, you would call it nanotechnology. And I'll get to some places where it used to be just kind of regular, product development, but now that is also requiring a lot of tools from nanotechnology. So yeah, this would be a subset of the larger piece, but much, much more focused. Okay, anything else? All right. Yeah, go ahead.
It's 10,000 steps, and all of the steps are all very multiple. What kind of research is being done? Where are we focused on research?
Yeah, we'll get to some of those pieces along the way, but the main thing that I'll just, as a general term, is that those instruments are highly, highly optimized. So if you think of it like I think of it old school instruments, some of which you'll use this week, like there's a number of knobs, right? Here's pressure, temperature, gas flow, those things you're going to turn right here. Turning knobs to optimize is not science, okay? It helps science. We need it to do science, but it's not the science, okay? And decades of research has gone into the design of those reactors. So the challenge is if you have a brand new idea, and there are brand new ideas all the time, it's not you shouldn't do it because they won't use it. You just have to prove it can be compatible if that's required, or you're going to completely change the whole thing, and that when you do it, the benefit is bigger. If the benefit is bigger, then of course industry will do it. So it's more like your research needs to be in context. So the science you have to understand, the people in the industry, they're not just knob turners, they are extremely experienced scientists. They just don't have time to do it because they have to deliver a product, okay? And so that's how the product development and research go hand in hand. And still today, there's still not enough hand in hand between those two yet. And to do that, we need people who understand how to do them. Yeah. AI was not on the map when the CHIPS Act was passed and under development. So, I mean, it was around in the background. You'll see machine learning, AI as drivers, but not like it is today. That happened like halfway through, okay? And fortunately, it's not an unnatural, it's a natural progression. It just accelerated everything even further. And so I'll get to a couple of technology areas for where AI breakthroughs came through on the hardware side. It was really the release of ChatGPT 4 that really initiated and catalyzed this whole thing of all the attention to it. And then a very simple inference of like, well, then where are you going to get the hardware? And so suddenly NVIDIA is a trillion-dollar company, right? And AMD was already making money hand over fist, and now their future is even brighter. And I'll just seed it with like the advances in NVIDIA and AMD to have GPUs that are now like taking over the world is not in the fundamental transistor or the integrated circuit, the leading edge piece. It was in advanced packaging. And that usually, and when I started research, it was a boring topic. And now it's like where all the action is. And I'll explain why that's the case. Okay. All right, those are good questions. Anything else? Yeah. They're already nano. We reached nano in terms of nanotechnology definitions like in 2000. Yeah.
I used to work in a fab.
Mm-hmm.
It's like, I don't see a lot of micro electronics based apps. So everything is on the nano technology right now.
Yeah, if you want to have a business,
Yeah.
for sure. Yeah. There are, but like at a teaching level, at the concept level, of course, those are all better. There are places where there are micro more needed than nano, for economic and business reasons. So like if you want to do 3D printing, 3D printing is not nano, it's yet, really it's not, okay? But 3D printing has a role, and screen printing has a role. They're not nano technically, but they're very useful for what they're intended to be used for, just not for devices of this complexity. Okay, yeah.
There any plans within the CHIPS Act or beyond to address supply chain issues? For example, a lot of the raw materials that go into chips
Yeah.
come from very few, something from one country.
Absolutely. There's a lot of panic about that right now, a lot of activity. So a lot of that initial efforts are in like at the State Department. So they have a $2 billion program, $200 million program of gathering like-minded aid of countries around the world to both identify and to share how to maintain raw material supply chains. So that's one big area. Second one, of course, is can you replace them with something that's less rare. So that's a very big area of research, and that's one where, of course, you need to really think carefully about its compatibility with the actual system and the financial model. Not an easy feat at all, but certainly that's an active place to talk about. Anything to shrink the number of steps is going to be valuable. Anything to have devices use less energy, which involve a lot of different kind of materials, is also important. The sustainability, both financially and environmentally, and energy consumption of these devices and these factories, fabs, is also in play, and a lot of the rare earths are involved in that too. So just one more number. So if Amazon, Microsoft, the hyperscalers want to build a new AI data center, and magically there are enough NVIDIA chips to buy, and they didn't have to worry about supply chain, in the best case situation, each data center for AI would cost $4 to $5 billion and would probably need the power of a mid-sized city to add to the grid. And the ambitions, as you see, are crazy, right? So there is a lot of like, how are we going to generate all of this hardware that people want to use? Okay. All right, so just some quick pieces. So this is the breakdown for the $50 billion at NIST at Commerce. So it's 39 for incentives. And what that program is to incentivize companies to build fab facilities in the United States. And that has already happened. What has been incredible is that there's been more than $250 billion of private level investment even before the first dollar of the 39 billion was committed. So the intention of the act was not to just pay for all these fabs, it was to catalyze and seed it. And so you'll see announcements if you go to chips.gov, basically every couple of weeks, with the biggest ones already announced for Intel, for Global Foundries, Micron, those are US companies, TSMC and Samsung and others. So we've committed about $25 billion of the $39 billion already, but the industry has already committed hundreds of billions of dollars in the United States. So before the act was passed, then Intel had already announced a $40 billion investment in Northeast Ohio to build fabs there from scratch, for example. Probably the first one to come online in 2026, 2027. Okay, but and so one misconception is that we didn't pay for the fabs with government funds. The maximum amount of the government cost match for those building projects is 15%. Usually they're about 10% or less of the total cost. The second program, R&D, $11 billion. So the incentives part was to bring manufacturing to US now. It was quite a high level of urgency, going from 0 production leading chips to, we hope, 20% by 2030. Okay, that's a very aggressive goal. The R&D value, what our job is to make sure those fabs stay in the United States and can continue to thrive. So in this industry, when the technology has to change every 18 months, okay, just think about your own dissertation work. This whole industry has to make a big shift every 18 months. And within every time they shift, there's new technology being developed. So we need to build an R&D ecosystem that can keep the fabs here going into the future indefinitely. And I'll go through how we hope to do that. And $11 billion actually does not go a very long way. We need also a lot of co-investment from the private sector to be able to accomplish our goals. Okay, but that's how they work together. We work hand in glove together, and it's a short term, get it here, long term, make sure it's valuable to stay here. And we have a 5-year runway to prove that we can make this happen. Yeah.
What's the high end, I guess, that you think that would actually make it possible?
We don't really have a number there. We just know, so we can use a reference point, for example. So, so IMEC, does anyone know what IMEC is? IMEC, okay, IMEC is a independent nonprofit research institution located in Belgium. That is basically a place where industry goes to work on their next set of as a research environment. So that one institution, which is a smaller scope than all of this, is running about $5 to $10 billion a year, and about 20% public ones. And so that gives you a sense of scale. So like 5 to 1, it's not crazy. That's like a norm over their 40-year history. And then it really depends on what value the industry gains from it. So it's not really like a government number. It's really what the industry will be able to, what we can do to get the industry to help us with these goals. And then we need to sustain over time. We had an effort like called Semitech in the 90s and 2000 where the US industry got together, and then they closed shop in early 2000. Okay, and that's due to a lot of changing business factors and some governance factors, but that's a different kind of discussion. Okay, but these two work together. There's programs in the DoD. Most close to us in R&D is the Department of Defense Microelectronics Commons. So these are mostly university-based resources to try to link together to address DoD-specific technologies. They're like quantum, edge computing, security. Underpinning all of this is workforce initiatives. So the industry, with their investments, they cannot find the workers that they need. There's a gap of hundreds of thousands of workers given the current pace of STEM education in this country. And so there's a huge level of opportunity as well as a tremendous need. For us in R&D, the basic part for workforce initiative is, as you'll see, is that we need to invest in people. Like people have the ideas, people make things happen. Okay, so the top 3 goals for the R&D program are pretty straightforward, but they are very, very important. And they're not really built around traditional like fundamental science research type of programs. So the first one is US technology leadership. So what that means is that this program, our effort, needs to be able to produce the capacity to invent, develop, and prototype and deploy the most important semiconductor technologies of the future. So if we go back decades, then the US helped invent the plasma reactor. And so that's a foundational piece that's inside in semiconductor manufacturing. And so what's the future plasma reactor? Then we want to be able to identify it and to invest in it. And there's a huge range of technologies like that. So what we end up telling academic communities is that the metric of success for this part of this goal in our program is not the volume of research. It's not publications. It's not even whether your research was really good, okay? The metric is, did it lead to a US technology leadership in a foundational technology? That's less about like dissing on science and more about expressing a priority for where we need to direct it. Okay? The second one is accelerate ideas to market. So we want the best ideas, the ones that reach the leadership capacity faster and cheaper. It is extremely expensive to take anything to market in semiconductors. So the Apple M2 chip, Apple didn't even make it. TSMC made it. They did the design of what they needed to make for their business decision. The M2 chip cost about $500 million, $600 million just to develop, and they didn't even invest in making it. And so TSMC took on those costs. And so you can see like just one chip like that is how much it costs. There are certainly many places to where we can make it cheaper, especially during the R&D cycles. And so we'll be trying to provide resources and programs to address that. As researchers, what it means is keeping that in mind, because the manufacturing process is never divorced from the discovery of new materials and components along the way. The last goal is to build the workforce, and we need the full range of workers, from the technicians to the new entrepreneurs that start the next NVIDIA. And so because people have the ideas and people take them to market, then we are really investing in the American people and those who are working with us. Okay, so the charge is we need to build a national scale innovation system, ecosystem that's targeted to this problem. Second is we can't build this all at once, so we have to build it in stages and to adjust as we go along. That's the only way to do it on the timetable that we have. What it means is we have to invest in the interfaces, which means handoffs between, say, an organic and an inorganic material, or a manufacturer and a materials developer, a tool developer, and a software developer. So this program is awesome. MGI is a huge model inspiration for what this can look like. But even then, we did not invest enough in the interfaces to connect things together. Okay? You know, our best connecting thing between different ideas and disciplines right now is still people. Okay, so that's what it takes. Last one, right? People make this work. Okay. All right, so I'm going to run through the programs. I'll try to hit the highlights where your background would be very aligned very well, and then save some more time for questions at the end. Okay. So we have 4 major programs, and so they're very different in character, but they are intended to work together. So we go on the left here, CHIPS National Semiconductor Technology Center, NSTC. Basically, you should think of it as like a paradigm-like activity, a public-private partnership with industry and academics and government working together on common goals, a common public-private partnership model, except much, much bigger, with much bigger ambitions with a national scale. Okay, we haven't quite attempted that before. We built a purpose-built organization to become this new institution. It's called NatCast. It was officially founded in February. So it's only been a few months, and they are off and running. We have communicated we intend to invest at least $5 billion into this institution. Okay. The second program is Manufacturing USA. It's already in an existing network of public-private partnership. It's also a public-private partnership, but it's focused on manufacturing. And what we have announced is the topic for this Manufacturing USA Institute is digital twins, of which your skill and MGI will be very tightly aligned. Okay. The notice of funding, we're planning to invest at least $285 million. They are required to match it with private funds, at least 1-to-1. So it will be something like a $600 million institute, very large. And I'll get to more details about what that is, but it's around digital twins. It's a public-private partnership. It is currently actively under competition. Maybe some of you are involved. The third program is the CHIPS National Advanced Packaging Manufacturing Program, NAPMP. And this is much more like a traditional, more like a DARPA program. The charge is that we need to develop a domestic advanced packaging system in the United States, starting from 0. We need to do it in 5 years, within 5 years. And that's entire space is where most of the performance increases in semiconductors and microelectronics will come from. So we're investing at least $3 billion into this program. And I'll say a little bit more about what that looks like and why we're doing it. But those are the targets. And then the CHIPS metrology program is really building and enhancing the core NIST capabilities around measurement science. So we have we're investing about $500 million in that activity. And I'll go through what that looks like. Okay. There are materials related challenges in all of these different areas. They are all over the place. They are not unified or harmonized very well in the industry very much right now. And so activities like Paradigm really have a chance to be able to try to find a way into what can be offered. Okay, so we are moving really fast. So when I started as the acting director, just a quick story, when Lori Locascio asked me, and Jim Olthoff, who was the lab director, associate director for lab programs at the time, asked me would I help stand up this program. I had just spent a year helping prepare for it, and I thought I could do it in my spare time. And I asked someone to help me to come do this, and that person came in the next day and said, I've dropped everything. What are we gonna do? And I said, what, you dropped everything? And then he just looked at me like I was an idiot, because I was an idiot at that time, and then just thought about it for a few minutes and it was like, I have to drop everything. So that was how we started. Okay. But we have been moving very, very fast. We've gotten lots of help and lots of support. We have pushed every government process to its extreme limits, found many new ways to do things to meet the expectations of the country. So just going from the fall into the spring. Spring for us is June 21. That's how we're literal on that part to buy us ourselves time. But each of these programs plus a standards activity have all been targeted to those top 3 goals, and just a ton of things have been happening. A lot of active funding opportunities on the street, and we're just barely getting started. Okay, so NSTC, public-private partnership, it should be seen as that's the place where semiconductor innovations come from, is basically where it comes. You don't need to know all this mumbo jumbo on governance. It turns out it's very important for success. A lot of the earlier attempts for government industry to work together like Semitech were failures because of governance problems, not technical or financial ones. The main thing for you all here is this, is to worry about the programs, other CHIPS R&D programs, and this part, these two, their facilities and their programs. So very much like Paradigm has facilities, try to take that and scale it to a national level. That's kind of the same basic idea. They want everyone to join. So if your organization hasn't contacted them to just express interest, then please do. So the first parts of the programs, this is kind of the full range of what's envisioned. It's written down in a vision and strategy paper that we published last spring. It has all of these components. They're drawing from ideas from across best practices of this type of activity in the past. We also asked the Presidential Committee on Advisors for Science and Technology. CHIPS has an industrial advisory committee. These are like CTOs of major corporations, the lead person at Intel, lead person at Global Foundries, and they've all committed, say, 3 to 5 hours a week in their busy schedules to help us do this well. And so there's a lot of excellent input into it. So you can read that to find out more about how it's going to go. Now, the first 3 things that have been announced by NatCast are, number 1, funded research. So we have 2 programs that were announced. One is on AI-assisted design of RF integrated circuits. There's a proposers day on Thursday. And so that's local. You can also see what's going on that side. The Workforce Center of Excellence is around training and building, basically pulling all the different activities across the nation already to amplify and make them better. That also is active right now. And then coming shortly will be an infrastructure announcement about how we're going to be building facilities, not research level like they're available here, but more like prototyping ones that will help you take a concept into likelihood for manufacturing. And so those are very expensive enterprises, but we want everyone's input into that. And then a whole bunch of other stuff. Okay. All right, I'm gonna run out of time. So Digital Twin Manufacturing USA Institute, I will just say this is a very tongue-in-cheek way of, but actually real way of describing it. It's basically an MGI level approach to this massive manufacturing problem. The entire industry recognizes that digital twins and using a virtual environment to develop new ideas and to optimize processes is far more cost-effective and time-efficient than not. I think this group should already know, you'll find out by the end of the week just how hard that is to do, even on a basic, like simple device level, much less this crazy manufacturing process. But the ambition is, if we are able to create a digital twin of how manufacturing works, whether you need the detailed chemistry and physics and transport properties, all the way to, yes, knob turning and optimization. Then in a shared environment, what's the biggest piece is that missing is that one process tool doesn't work interoperably with another process tool. I'm sure you've experienced this already. Like your electron microscope file is not compatible with your software and you have to find a transition. And these type of things happen all the time. So we're able to create a shared experience of having interoperable data, interoperable models. Then we can start to invent virtually manufacturing processes for the industry to invest upon. And so you can see we need a physical facility for validation. You're about to do that this week. We need a virtual one with projects that are high impact and valuable. That's been done for you. And then you need a digital twin that pulls it all together so you can start to iterate and come up with the next idea. Okay. So there are active proposals on there right now. These teams are huge. The industry is highly mobilized. And a digital twin environment that lets you do fundamentals all the way to a chance to put it into manufacturing is a major competitive advantage for the country. This is not being done in other nations around the world. Okay, so for the packaging one, the main thing here is that we are going to really do our best to make a viable advanced packaging industry in the United States. I see you have an expert coming in, so if I don't answer your question, then Professor Spector can do that for you. Now, what I said before is that all the advances in AI chips today have really come from advanced packaging. And the dream of advanced packaging is that instead of the old ways, which is like you made a chip and you just got to protect it from water and from air, and you have to connect it to a printed circuit board. Okay, you can do that. That was all done afterwards. But now you have highly specialized chips, like a GPU next to memory, next to a CPU. And you have all kinds of new CPUs being invented. So now you want to put them closer and closer together so they can optimize collectively as opposed to on one gigantic piece of silicon. Also, manufacturing one big piece of silicon is insane. So wouldn't it be better if you could break it down and then put things together? And that's what's the promise of advanced packaging. Now, any of you have done an engineering project where you have to like build a vehicle or like a circuit, there's a huge amount of engineering challenges. And so if like one example would be maybe you have a very cheap chip and then you put it all together with advanced packaging and then your little cheap component destroyed your NVIDIA chip. That's really not a good outcome, right? And so how power is distributed, all kinds of problems and all kinds of new technology have to be invested. So TSMC, Intel, AMD, all of them are investing in advanced packaging to try to get to those performance increases, and the continuation of microelectronics devices performance, including expanding functionality into power and into other areas, is going to come through that. So these are the main different parts. So there's a lot of roadmaps. They're like old roadmaps. They're very dense technically, but a lot of exciting problems I think you can find. We're going to invest in those technologies. We're going to build a prototyping part. We need tools to be able to put these things together. They're called chiplets and chiplet design packages. And then we want to design and build that in the United States. So there's a lot of components to how this program is put together. You can read the vision and strategy paper. We expect to have a major announcement by the end of this, actually Tuesday. Tuesday we'll have a lot more detail about what's going to happen here. 9th is tomorrow? Okay, tomorrow. Okay, metrology, I'll just say that there are grand challenges. These are like very fundamental measurement problems. There are things like, can I measure the size of my nanometer device in 3 dimensions within a second in real time? Because if I could do that, then our digital twin, our manufacturing, and our science would be a lot better. Well, that's a crazy thing right now. At NIST, this is part of one of my last hands-on lab experiments, working in experiments, was to invent a way to do that. Unfortunately, it comes with a synchrotron. And so you need a synchrotron to do that. But there are ways to get past that. But these are the kinds of problems that are being worked on. So there's 7 of them. Each one of them has decades of research to do. So, you know, There's one that's modeling and simulation. So, I invite you to read the Grand Challenge paper off chips.gov if you want to be inspired into what else is possible. The last thing I'll say about metrology is that we plan to learn from our MGI experience and to build a digital platform, a metrology exchange, where we intend to take all of that research in the metrology space, as well as across chips, and to make it fair and to make it shareable, and to do it with industry in creative ways where we want industry to tell people what they have and what they know, but we don't want to make them share it. That's actually very, very valuable. So then a marketplace of ideas and how it can be deployed in multiple different modes, you just need a platform to do it, and that's being built right now. It's called Metis. It's the Greek goddess of knowledge, I think, and innovation. Okay, so there's 4 programs. Each one of them has a very important materials design component of it. For this one, I'll just name one more, which is called co-optimization. What that means is as you design a new device, you also look at the manufacturing process and you design both of them concurrently. That's how industry is doing it right now. Okay, so like one last fact, if you read a history book about how the semiconductor came to be, the most popular one is called Chip War right now. The most fortunate decision by a historian ever on a topic to pick to write. It's written in a very engaging style. It's very dramatic. It talks about the people involved. But in the early days of semiconductor industry, there's maybe 5 elements that were used, and today there are hundreds. And so it's just been crazy. The introduction of copper as a wire took about 20 years. And now that timeline has just been blown away. Okay, so you can go, chips.gov has all of our details. You can read them. You can sign up for a weekly newsletter to find out what's going on. They're short, so you can just see exactly what's happening. We have a bunch of email addresses to just go ahead and ask questions, and my email address is there too if you want to reach out to me. Okay, so I hope that was useful, giving you some context. Didn't go into much detail, but I'm happy to answer questions or response because you'll have me.
So thank you, Eric, for the wonderful talk and overview. We do have another question from online. So the question is, what can undergraduates contribute to at NIST out of college versus what can they contribute to at NIST with a PhD or higher level education?
Sure. So we recognize that post-baccalaureate is it's also an important time. I mean, you don't want, just like in building the STEM workforce, you don't want people to be weeded out in 6th grade. We want people to come back and to explore. So right now we do have like a summer research program, just like Paradigm has. It's called SURF, S-U-R-F. So I invite you to look at that. The deadlines are around January. We are looking to build a post-baccalaureate program in CHIPS metrology. So that hasn't been launched yet, but I'd invite you to pay attention to the CHIPS metrology part and sign up for our mailing list. That's a place to do that as well. In the NIST culture, it's not just a NIST culture, we're literally in public service. So we work for the public. So if you have a question, the rule I always had and was taught is that we answer every inquiry, even the crazy ones. And so, so if you see an area you're interested in, there's contact information. You can start to reach out, or you can reach out to me and I can help connect you with the people you might be interested in.
Well, then I got another one from online.
Okay.
So and it's related to sort of evaluation, I think, of the CHIPS Act program. So what key performance indicators and methodologies are key to tracking the impact of the CHIPS programs on the national scale? Is it products, patents, startups? What are the metrics?
Yeah,
Do you have metrics? And if so, what are they?
There are, we do. There are, there's quite a list of them, but they also are not like static. Okay, so for example, and in research, it's hard to do that, right? It's not like you want to just, like in Silicon Valley, number of unicorns is kind of a metric, but not really. Like that might be a target even, but it's not really the first ones are going to be in participation. So did people sign up? Did we actually provide them value? Did we actually identify a pathway for leading edge technology that we got everyone back together on? So I think we have a lot of them. Did that resource actually help people? Like are people are using it? And then we will go into more metrics about the performance overall. Like it'll be much more sophisticated analysis of the landscape and the US position within it. And some basic ones like, did a product get to market? That is true. But we also, more importantly, want to know how much it would have cost or how long would have taken without the CHIPS Act. That's more of an important metric for us. But that obviously will take time to do so. The biggest participation one is on workforce. We really need to generate the industry interest, align it with the academic activities. They're not fully aligned yet. And so that level activity will be important as well. So you can just imagine what came out of the top 3 goals, go down a normal logic tree for what that looks like, and you'll probably end up in the same place as we did. Yeah.
I guess you were talking about like a 5-year timeline for something for success, and then also talking about like a 5-year timeline for things to happen. I guess, so is they kind of like putting it, I guess, are there like redundancy plans? I mean, like how much of this cannot go wrong or like not work? This seems like
Yeah.
everything had to work.
Yeah, failure is not an option. That's one. So it is a very interesting, that's a good question. We get asked that a lot too. Basically, the answer is, like the incentives program is for 5 years, Commons is literally for 5 years, funding and the government for special things like this is on a 5-year window. We do and are allowed to spend the money longer, okay? But we're doing something very different. So all those factors you just named. So the answer is we have to demonstrate value within 5 years. And we should have a better idea about what it would take to sustain that if we are successful or when we're successful. And we don't really have a clear idea of what that looks like. And no one really wants to make that commitment until they can see what it does. So we need these leading indicator parts, and then we hope to make that case later on. So that's also learning about just the politics of the country today, as well as the realities of just government funding overall. And so 5 years is actually a pretty long period of time relative to year by year that we're living under right now. But it is short enough that we are working very hard and assessing every day on whether or not we're making a difference. And so at the end of the day, you don't earn the next level set unless there's a demand from the public for what was most valuable and to continue. We have a lot of models. We have a lot of advisory people. Our industrial advisory committee is constantly worried and helping to think through what that looks like and helping us think through whether or not we're doing that. So, yeah.
Okay. Last quick question. Yeah, that's great, Aaron. Thank you. I was wondering, when you think back to sort of what got us to the point of needing the CHIPS Act, dropping from 7 to 12% and so on. This will fix so many of those things. What prevents market forces in the future from again pushing us down? Does anything inherent in chips, or is that going to take the follow on to sustain that innovative fund?
The biggest realization is that market forces don't often align with national interests. That's why industrial policy was now embraced because of that interest overall, both economic and national security. The other part is that because semiconductors are so foundational to enabling everything else, then it has a special definition for what. So those are really the more important ones about what has changed and what would be needed to sustain. Then the big question is, what is the most effective and most efficient way to invest a public investment to accomplish those goals? And we're about to learn a lot about what that can look like. The answer has to be that it's partly the nature of the business ecosystem. So that's where market forces need to be understood. So if you read Chip War, you'll see a lot of the current problems we call problems today were very seen as highly sophisticated, smart business decisions at the time. So most of advanced packaging is in Southeast Asia, like Vietnam and countries around there. And the reason for that is because a very smart enterprising person at HP said it would be cheaper there and just moved it there and took advantage of Japanese production methods. And that's why it's all there. for 30 years later. And so there's a whole bunch of things like that. So if you understand or just see how the market parses both work or don't work against the national interest, then that's what's going to be more into the future.
Okay, so thank
Okay.
you again.
All right.